Welcome to the LEAP seminar. Our speaker today is a colleague at LEAP, Luis Seabra. He is member of the Atlas group. So Luis studied physics engineering at the Faculty of Sciences of the University of Lisbon, where he obtained also his master's degree, working on the construction and performance tests of the alpha detector for the Atlas experiment. So after this was done and the detector installed, Luis kept on working on the operation and is fully responsible for the detector control system since 2013. So he also put this expertise in control systems into practice in other subsystems of Atlas. So the tile colorimeter and also the Atlas forward proton spectrometer, where he has deputy coordinator role since 2015. So this Atlas forward proton control system will be the topic of his seminar today. So Luis, please, you can start when you wish.
Okay, thank you very much. Thanks for the nice introduction. So, okay, so I will start by define what is the detector control system, just a brief introduction. Then I go through the WinCC way, which is the tool where we built our DCS. I will mention also what are the detectors in Atlas Roman pods. And then I go to DCS overview, all the system involved, operation aspects, and also data and archiving stuff. Okay, so what is the detector control system? So in almost all papers, articles related with DCS, this paragraph is the most, with a few changes, most used, which is the DCS provides control and monitoring of the detector hardware and ensures the safe and reliable operation of the detector, assuring good data quality. So what this means is that the detector should be able to bring, the DCS should be able to bring the detector into any desired operational state. It should be able also to assure a large variety of system integrated with enormous number of individual channels controlled and monitored, and also should signal any abnormal behavior, like a temperature out of range, something like that, and should allow also some automatic actions and manual also, and should also handle communication between Atlas subdetectors and all independent systems like LC accelerator, detector safety system, etc. And in the end, it will be the interface between the operator and the detector. So the WinCC way is the tool chosen to construct our DCS, which is a supervisor control and data acquisition system. It's a product from Siemens, which previously was had the name as PVSS. All people know more about PVSS than WinCC way. And it is what we use in all ELHE experiments. It's composed of several, as you see in the picture here, it's composed of several layers. We have the driver layers that connect to all our front-end system. The communication layer is responsible for the data storage and also for the connecting to other systems, like I mentioned before, the detector control system, LHC accelerator, etc. The application layer I will mention in the next slides, and the user interface layer is where we interface with the user. Okay, so this is the project console where we for the DCS, where we have all managers that are responsible for the work of the DCS. I will just briefly mention the three of the most important, which is the control manager, which is able to execute simple or complex scripts that allows to operate the detector mostly automatically. It's based on C, and it triggers on events, like if voltage is changing, then the script will check if there is something to do with it or not. It uses a large libraries of functions. The API manage is the application programming interface, which allows to incorporate the compile call, which is mostly used by other processes here, like the process monitor and event manager. This is all API managers. And the driver manager is the in the lower level that is mostly for the communication protocols like OPC, these open platform communications, and distribution managers, and communication with the PLC through a S7 driver, and so on. So I'm showing here how our variables are presented. So they are organized in the data points, which represent a channel. For example, I'm showing here a channel in the high voltage, and then below or part of these data points, they are the data point elements, which are composed of for example, here we have the voltage measure, currents, and so on. And in these elements, we can set the address, archiving, any kind of configuration, including the alerts. The alerts are a very important part of the detector, because it signals when the variable is out of range or it's in a good range, and it represents the status of the detector. It also have these different levels that I'm showing here. So for the graphical user interface, we use it to show all the parameters that we read, and we can also execute some tasks by user commands. In the beginning of detector construction, we use what we call technical panels. We put a lot of information on them. We also use them to send commands and for debug tests also. And these are mostly for an expert use, because they have a lot of options, as I'm showing here for a vacuum system. Sorry, a lot of readouts here I'm showing, then also possibly to set a lot of things. These are mainly in the beginning of the detector used to control the detector, and they are sorry, the base to construct the panels that will be used in the FSM. The FSM I will mention in the next slide, but for now, the FSM is panels are the panels that are going to be shown to the common user that doesn't have any action available. It's just some information on them, and I'm showing the two top panels for the AFP and alpha. Okay, so we have a lot of panels that we can operate the detector and show all the information, and these are in part multiplied by the number of detectors that we have. So we are able to monitor everything and control everything, but using panels we lost a bit of where we are, and in fact we could have the risk to not monitor and control anything. So for that we use the finite state machine, or FSM, which is an abstract representation of an experiment. We use it to control and monitor a huge number of parameters. And we have what we call the front end, which is correspond to FSM device units, which calculate the states and the status of the components. So the states is based off the component states. Like, for example, one channel is it's on or off, and the status if there is an alarm. So I'm showing here a state here in this picture, a state of the detector, in this case alpha canvas 1, which is shut down, and it's showing here a status which is an alarm with an error level. In the bottom of these, so for the front end items, we have also defined commands that will that can operate the elements. In this case, alpha canvas 1. So the DCS backend, it's mapped into an hierarchy of FSLM elements, which are in top of these front end devices. So, for example, if we show here an error in the front end, it will be propagated upwards into the FSM structure. So the status propagates upwards, the state and the status. And when we want to send a command, in this case, for example, if we want to look in here into the high voltage, if you want to switch on the high voltage, doesn't make sense to go item by item by switching on the high voltage. We do it by sending a command through the FSM top and then propagate it downwards the hierarchy. And this is how we propagate and control, monitor everything from the DCS side. So this is how it looks, our FSM and panels combined. So in the right top, we have the navigation options, and where we can go through until we reach the most basic elements. And here we have the panels where we have the description of the detector. Of course, when we go down the hierarchy, the panel also change to reflect what we are seeing. Okay, so Atlas Roman pods in fact means alpha plus AFP. They are two separate detectors, very similar. So that was the basis for grouping all together in RAP. So organization are the same, and people work also in both detectors. We have many of them, not all of them. So formally responsibility, it's fully in case of the alpha DCS, and the deputy coordination is for in the AFP, where we contribute to the movement, vacuum, and cooling system. So Atlas Forward protons is composed of two stations of each side of the interaction points, to 200 and something meters away. In the closest station, we have only one silicon tracker composed of 4 silicon sensors. In the most far station, we have the silicon tracker plus the time of flight detector. This is used silicon tracker. We want to make tracks from the protons, and the time of flight want to tagging them. So both of them are inside a Roman pod, where we can see here both of the detectors. They go inside the Roman pod, and then we go to one station, and they move horizontally closer to the beam. Alpha is a bit different. It uses again the Roman pod, but the system is different. We use scintillating optical fibers arranged in a UV shape, where we have here the active layer, and it's composed of a lot of them. The fibers are going to be read out by photomultipliers. In this case, multi-anode photomultipliers. where each fiber will go to a single PMT channel. So there are 32 channels for each PMT. Okay, so it's composed of the main detector, which is here this diamond shape. Here in the picture, it doesn't show the overlap detector, but it's made basically to calculate the distance between two detectors, the up and down detectors, because they are going to be inserted in these Roman ports here and then go to approach the beam vertically, one from each side. So for an overview of the DCS for control and create our DCS project, we will use one machine with a single OPC UA project running. There are interfaces for communicate with the hardware. That can USB interfaces. We are using a Linux 67 operation system together with the latest version of WinCC UA. We will read a large variety of systems. So it's showing here some, for in case of AFP, the movement, cooling, vacuum, high voltage, and so on. Alpha has a lot of this system as well. And here I'm showing here the organization in the FSM. Not in FSM, sorry, in the DCS backend and front end. So for AFP, you have one single machine, which is in the local control station hierarchy, and then we move to the sub-control station where we have the other Atlas sub-detectors. And because we are small in terms of number of projects running, we are all AFP and RPO, which is in fact Alpha. We are in the same group, which is the 4 detectors. And in the top, there is Atlas Global Control Station. For this, we have all connected to the bases, the DCS security system, and also the TDAC system. I'm showing here the hardware provided by the DCS. In this case for AFP, Alpha it's similar. So in the UC15, which is an Atlas underground counting room, is close to the Atlas detector, where we have most of our electronics, where we have the Roman pot movement service, secondary vacuum and cooling, supply for the high voltage, low voltage, temperature monitoring, hardware interlock. This is for AFP, and also have all dedicated crates for the DAC system. So far away, we have our detectors. This means for us not something like the 330 meters of cables connecting to all the hardware. Because the AFP needs different kind of low voltage distribution, it's divided in 2 stages. Well, the first stage is in the USC15, and the second inside the tunnel. So whatever we can, we put in USC15. If not, we use in the tunnel, because we don't have too many space in the tunnel, and the access is not very easy to do it. Okay, so movement system for Alpha and FP, they are similar. It's what we use to monitor our Roman pot's position inside the LEC beam pipe. For FP, we have horizontal movement and Alpha vertical, both of them with 5 micrometers step. They are switches which allow us to have proof where we are, and also we use them for calibration. There are 2 system involves. There is a national instrument PX size for the movement, and there is a phaser, which is the front-end software architecture, which communicates to DIM and has also the DNS host. How it works is the CCC, which is the Silent Control Center, which are the ones that operate the dormant pods. They send information to move the pods. This goes to the phaser server, and then it connects to FPGA from PXI, and then interacts directly to the motors. From the DCS, we all just have access to the FPGA value, so we only can monitor them. But there are some action available for us, which are disable the movement and extract the dormant pods with spring in case of an emergency. But basically, the movement is done by a CCC operator. We have available 3 measure of distance from the movement system, which is the linear variable transfer, differential transfer, step motor, and a resolver. And every time there is a difference between the readout of them, there is an alarm, which could mention that there is something not going very well with one of these measurements. So here on the top bottom left, there is part of the panel where we can see the state of the movement, the position inside the beam, the switches here in, home, or out, and also the readout from the positions from these systems that I mentioned before. We also tag a good position, which is then sent to DAC, where we want the detectors to be in physics position. It's just something for data analysis to mention that we are in the good position. Here is the plot where we can select which position we want to define as a good position for data taking. Okay, so the DCS calculates the state of the detector also based on these switches and on the movement state itself. So here I am showing all the state that the movement will transmit. So not present will mean that we just disable the movement, and configure is something that was the motor lost the readout because for example the Roman pot was extracted by springs. The calibration is when we going to reach the calibrated switch with which is a calibrated position, and then waiting for commands. It's a normal state where we waiting for movement. Are we in or out? So here is the calculation of the state based on the detector state based on the movement state and the position in the switch. For in this case, I'm showing here a waiting home position, where we are the movement showing waiting for commands, and the home switch was pressed. Of course, for alpha doesn't take too much care of this. We don't care much of this, but for AFP, we have basically two states for the movement. We are ready when we are inserted, and we are prepared when the pods are in home position, but the detector is mostly waiting to be in the position for data taking. For secondary safety beam, it works as a protection against the LHCI vacuum and icing. Basically, this is more for AFP, the icing part inside the Roman pod. They are very similar systems, and provides independent vacuum for each arm. So for AFP, it's between 10 and 40 millibar, and for alpha between 10 and 20 millibar. We have it's a duplicated system for to increase the durability and cope with failures. So I'm showing here there is pump 1, pump 2, the pressure readout, and the valves as well. So how this works? So the pressure when I'm showing here several pumping cycle. On the bottom, you can see pressure increasing in the round pot, and when it reached the limit of these 40 meters in case of ASP. Here I'm showing here the pump pressure. The pump starts working, so it goes here to 0, and then the valve works, open, sorry, and then it starts pumping the air between the firing new station. And then when it reaches certify when we are happy with the temperature, the pressure, the valve is closed, and then the pump stop working. And this is all done by using the PLC, the programmable logical controller. So for AFP, we use a new PLC which communicates through DCS using an S7 driver. And Alpha, we are using a very old. In fact, we are the last of the detectors using this kind of PLC, where the communication it's only done using an old OPC server, and for that we need a Windows machine. So Atlas doesn't want any Windows machine, so we needed to run this OPC server outside Atlas network. So from I'm showing here for Alpha the vacuum and ventilation panel, where we can see some pressure values in the Norman pot and in the pump side. And the way it works is that we can set to work in alternate modes. First pump 1, then in another cycle pump 2. You can have both pumps working at the same time, or select one of the pumps to always working, or we can have a manual manual mode where we can just do it as we want. For AFP, there is an interlock from the vacuum system. It's a software interlock, where we can, in the case we lose completely the vacuum, goes to a very high value, we extract the pots automatically. And this is a critical system for us, so there is notification by email or SMS in case of an alarm. So for the cooling system, we use it to cool our electronics and detector themselves. Both systems have controlled by the same PLC used from the vacuum. Alpha use mainly the fans, and FP a system called the dry air vortex cooling system, which I mentioned in the next slide. So Alpha doesn't have any electronics inside the Raman plot. So we use it, a filler will conduct the heat to outside the Raman pot, and the ventilation is provided for the PMT box and the motherboard. This from the previous panel, I'm just showing here a bit the part that is responsible for the vacuum, the ventilation. Okay, so for the fuel, the cooling system is different because inside of the pots we have electronics, so it's not possible to put air in there because there is a safety vacuum system. So there is an heat exchanger inside the Raman pot, where inside of this heat exchanger there is air, cooled air running. And we, like I said, we control it by the PLC, and we have the ability to choose between two modes. We can use an automatic mode, where I'm showing here on the bottom plot the way it works. So here the cooling is working, and when it stops, it goes down the temperature in temperature, and then when it opens when it turns on again, it goes to the temperature as it works previously. So in the automatic mode, we use the PLC control through this proportional integral derivative, which when it's the switching off and on of this automatic mode, it creates a kind of wave effect that trying to stabilize the temperature, which for us it's the normal way to do it, because when beam from sometimes they are beams of different intensities and which represent different temperatures. So we want to keep all the same temperature inside the Raman pots, because it affects directly the normal function of the silicon tracker and the PMT as well for the time of flight detector. Okay, so power supply for AFP, we need to power the silicon track sensors and the time of flight PMTs. We use the ISAG edge voltage crates with two models which delivers different voltage. All of this is controlled by UPC server. And I'm showing here the plot where you can see for this example for the planes in silicon tracker, we have a minus 220 volts being delivered. There is a power supply for the Optolink. This is to provide power for the opto boards, and is also controlled by the LNB. The LNB, which is the general board created by Atlas for different purpose. And for the low voltage, there are two stages. One in the USA 15, which from Wiener power supply, controlled by OPC server in the internet. In this case, controlled. And the currents are measured through the LNB. The second stage is the low voltage regulator crate, which is inside the tunnel, which is CAN bus controlled through an LEB. And here we have a panel where it gives the state of this voltage regulator crates. So for alpha, we have also to power our PMTs, these multi-annus PMTs. We have 23 of them plus 4 triggers PMTs for each detector. So this is time 8. It's power also for high voltage crate, ISAC crate with 8 models, 1 for each detector. And this is CAN control through OPC server. You can see here a part of the a panel where it set different voltage for the PMTs for each for the different type of PMTs that we are using. So for the low voltage, we have three elements. So we have 2 front-end crates providing 5 and 7 volts to the motherboards. We also have 2 rectifiers, which regulate the inputs for the front-end crates. 2 controllers in the VMing crates that allow to remote control and monitoring of the front-end crates. And it's Ethernet controller with OPC server. Here there is a part where we can see now it's off, but it's where we can see how much power is delivered to these motherboards. Okay, so for the AFP temperature monitoring, we use temperature sensors called NTCs, which are inside the pots, in the walls, silicon tracker planes, and heat exchanger. In the station, there are some in the stepper motor and local trigger boards. And there is also in the air cooler, opto board, and voltage regulator crates. They are CAN bus monitored through the LNB, and they are connected to in the interlocks matrix crate. And if any alarm comes from this temperature monitoring, there is an hardware interlock which shuts down the high voltage, low voltage, or whatever system is causing an alarm. So for alpha, we don't have any hardware interlock. We just collect temperature from inside the pods and in the station, and also in the VIP pipe. The monitoring is exactly the same, but we just store them values and have alarms defined for, and anytime that there is an alarm, the operator knows if what action should do or not. For the RAD ones, it's the radiation monitor. We only have one side to have a feeling what radiation we are getting. The readout is done every hour by a control script, and they are monitoring to the CLMBs that we use to control the temperature. So here I'm just showing a general hierarchy of the FSM. So it's where we have our hardware and how everything works in our system. For the alpha, the RPO, it is divided in 4 stations, and if you navigate through them, you can access all of that that I mentioned, the high voltage and movement systems and so on. And the FP is also the same. In this case, the organization it's different because we divided in ARM A and ARM C, and then we get near and far station. And the difference between near and far is the fact that we have here the tough part with high voltage, low voltage, and so on. So all of them can be accessed through that I mentioned, and can be accessed through the FSM, and we can visit each part in case of an alarm or something needs to be debugged and so on. So for an operation point of view, AFP runs continuously with Alpha, with Atlas, taking data when the AFP is inserted. So basically, AFP is always on, but Alpha only runs in low luminance that he runs. So it's mostly off during the year. Alpha has also a very complicated power on procedure, which takes several minutes. So I'm showing here the state from the FSM, which gets different commands depending on the state that the detector is. So we need to propagate all the time the ready state, because even if the detector is shut down, which is the case of here, we don't want to propagate the shutdown state to the FSM to get to the Atlas. So when we switch the motherboards to on, we go to this state, which is front end on. Then we move to what we call the PMF configuration, which is the PMF. It's the PMT front end. And then when we switch on the high voltage, we get our system ready. So what is this PMF configuration? So it's the configuration of 23 FPGA, one for each PMF, and 2 FPGA in the trigger mezzanine. So it has a user interface dedicated to this task, where we can see the progress of the configuration and check for failures. Basically, we are sending data to the FPGAs concerning for the the PMF gains, thresholds, and control bits for each PMF. We also send the trigger pattern, rates, and latencies, and the LED configuration in case we want to run in standalone mode, where we can set the pulse width, voltage, and this mode is just which kind of if we want working or not, because when we want to work together with Atlas, we don't want the LED flashing. This is done through the LNB using the serial peripheral interface, where we change 16 bits words between LNB FPGA. There is a readback test of what we send. So we send all the data to the FPGAs, then we request the data to be sent again in order to check if if the configuration went well or not, because there were in the beginning some issues with these configurations. As you can see here in the panel, they are all green, so they were configured. In case the readback fail, we get an orange, and we are configuring the authorization, so we have information coming from this panel. So during this configuration, we cannot perform a motherboard monitoring, because we basically use the same CAN bus cable to monitoring the motherboard and also to configure. So CAN bus doesn't like to have different configuration information coming at the same time. So we'll get some noise and configuration will not work. So for archiving, we archive all relevant data in the detector operation. We use smoothing mechanism because they are variables that doesn't change too much over time. And we store this data into database. So we use an online database, which is in Oracle, which is available out inside Atlas Technical Network, which is give us online monitoring, as I show in here in these two plots. For the top plot is the temperature inside the tunnel for alpha, and also here is the temperature for the different places in the silicon tracker. For offline database, it's stored in Cool, which is available outside Atlas Technical Network. This is mostly done used by physics analysis. We also have a tool available for us, which is the DCS Data Viewer, which is very useful tool where we can check all of these, including some alarms over time, state of the detector, and so on. For the critical parts of the detector, which we want to monitor, we define some notification where we can get some emails or SMS with information how it's based on triggered alarms. So for data analysis, normally the data from DCS is stored mainly for hardware debugging, but there are some studies that can be performed. There is we don't do it because we don't have manpower for it, but we can try to see the relations between pressure and showers, the pressure for the secondary vacuums, because the Roman pot where the beam will pass close the sensitive part of the detector is composed by a thin window of aluminum, and this window will bend according to the pressure. So it can provoke some showers, but this is not proven. And also temperature can provoke showers, so it's that thing that could be done based on the temperature. And there is also the impact on the silicon track efficiency concerning temperature and high voltage, because they are not the same during time. So as final remarks, WinCC way provide us all the necessary tools for the data points variables, so alarm, archiving, etc. We are able to use our control scripts for automatic actions, and we can use also the FSM and the graphical user interface to operate and monitor in the detector. So now the ARP DCS is able to control and monitor a large variety of systems, which is the big challenge of this DCS. It's fully integrated in Atlas DCS, operating continuously without any big issue. It's able to coping with Atlas upgrade in terms of software improvements and maintenance. It's attending all wishes and new requirements that all the collaboration is asking, and is able to provide support, DCS support, during data taking, or well, all the time, not only in data taking. Okay, thanks for your attention.